In this video, we'll look at how we can create analog-like signals from our Arduino using a technique known as pulse width modulation, or PWM. From earlier videos, we know a digital signal is a discrete voltage, and typically 0 or 5 volts, whereas an analog voltage is a continuous voltage. It might be, for example, 2.5291 volts, so on. Sometimes we need to create an analog voltage from our Arduino to control something. For example, if we want to dim a light, digital on or off doesn't really cut it. That's of course unless we do that on or off really quickly, so that it looks to us like the light is dim rather than just flashing on and off really quickly. This is the basis of pulse width modulation, or PWM. We're turning something on and off really quickly and hence create an analog-like voltage. If we do a bit of filtering on it, it will look even more analog-like. This voltage isn't continuous though. In the Arduino case, we have 256 different voltage levels that we can represent. Levels 0 through to 255 correspond to voltages of 0 to 5 volts. So, if we say 5 volts divided by 255 different steps, this gives us 19.6 millivolts per step. So if we move from one step up to the next step, for example, position 0 to position 1, this will give us an extra 19.6 millivolts. So we'll go from 0 volts to 19.6 millivolts and so on as we add each successive step. Now the basic pulse width modulation setup is we have a square wave. We alternate between high and low voltages, ones and zeros, and we have a constant period. So we keep our period constant and fairly fast, and we vary our duty cycle, the proportion of on time to off time, and this allows us to create different analog-like voltages. Now the code to do this, fortunately, is very simple. We've got a nice little function called analog write, and to that function we specify the pin that we want to perform analog writes on and the number between 0 and 255 that we want to generate. Here's a few examples of how we generate different voltage levels. You see that we can generate 0 volts by putting a 0 in the analog output field, and at the bottom 5 volts by putting 255, the full range, in the analog output field. And then we've got a whole lot of different voltages in between these ones that we can generate. And we see as we increase the value that we supply, the proportion of on time to off time increases right up to when it's fully on, when we get 5 volts. Now if we do a little bit of filtering, well, we don't need to do this if we're dimming lights because it flashes on and off faster than we can see, we can remove these highs and lows and these peaks and make it look a whole lot more analog-like. This is just some basic first order filtering that we've done on this signal. Now we can't use pulse width modulation on all the pins on the Arduino, only the ones marked with a P. So pins 5, 6, 9, 10 and 11 allow us to perform analog writes. We don't need to do any setup in the setup field. The analog write function does this all for us when we call it. So now let's write some code to give an example of how we can use analog write. What we'll do, we'll create some code that has a switch that will control what we're going to be using analog write for, and then analog write to control the brightness of an LED. So let's create some variables for those first. So our switch will connect to pin 5, our LED will connect to pin 6. In our setup, remember we don't need any setup for our analog write part. We only need to set up the switch. So we set that up as an input. And then we'll write our main function. And essentially what we're going to be doing is checking if the switch is pressed. If the switch is pressed, we'll set the LED brightness to be 75%. If the switch is not pressed, we'll set the LED brightness to be 25%. So we're checking if the switch is pressed now. And here's our condition for if the switch is not pressed. Now we need our analog write conditions. We'll be addressing LED pin, but what value do we put in here? Well, if we want the LED to be 75% on and our total value is 255, we need to remember also that for our LED to be turned on, it needs to be a low voltage of that pin. We put a high voltage there to turn the LED off. So we effectively want it to be 25% high, 75% low, and that will give us our 75% on duty cycle. So to work out what value that we need to put in there, we can say there's 255 different voltage levels there. We need to multiply that by 0.025, which gives us 61.25. So the value that we'll use will be 61. And we have to do similar for our 25% brightness as well. So we need it 75% high to give us 25% brightness. So 255 times 0.75 gives us approximately 191 when we round it off to an integer. So we'll put that in there and let's see how it runs on the board. So here we see our hardware setup for this exercise. We have our switch here connected into pin 5. We have our LED here connected into pin 6. And of course with our switch we have our 10k pull-up resistor, and with our LED we have our current limiting resistor as well. You'll notice along the edge here I've used one of these planes, one of these vertical planes for ground or 0 volts, and one of them for our 5 volt signal, and those wires just feed into the 5 volt and ground signals here. As all these are connected, it makes for an easy way to route our power and ground out to various parts of the circuit. So let's plug it in. I've uploaded the code already. So the code's uploaded. When I push the button, you'll notice it goes brighter. When I don't press the button, you'll notice that LED grows dimmer. If we connect an oscilloscope up to our circuit, this will allow us to see very quickly what's happening when we press the button and don't press the button in a graphical sense. We can see with the button not pressed, the duty cycle is 75% high and 25% low, and the LED's quite dim. When we press the button, the duty cycle changes to 75% low, 25% high.